We've been having a series of small conversations over the past few months about parametric modeling. And it started off as something that a few groups in the firm have been using, and it's starting to emerge as a broader interest. And so it seemed like this was a really nice time to bring in someone who can speak about it from a different angle. We're really trying to see it from all different angles and how it can relate to the work that we're doing here at HGA. And it's a tool that can be used as part of the planning process in architectural design, as an engineering tool, and also as a fabrication tool. And so here we brought in Jeff Baglio to talk about it from the fabrication point of view. And so Jeff's involvement is with a facade contractor called Enclose. And Enclose is really one of the premier curtain wall contractors in the country. And what's interesting is that they happen to be based here in Minnesota. So they have this really impressive history going back to really some of the origins of curtain wall technology. They were involved, either them or as their sister company, Couples, in really some of the most notable curtain wall projects in history. So Sears Tower, John Hancock Tower, Hong Kong and Shanghai Bank, Petronas Towers, Getty Center. The list goes on and on. And more recently, they've started to take on, and I would say sort of historically, just to generalize, those tended to be more kind of high volume projects with a lot of repetition. More recently, they've started to take on more projects that are smaller and more complex. And a lot of that is really being influenced by the development of these smaller groups that they have in LA and New York of the Advanced Technology Studio. And so Jeff is the Associate Director of the Advanced Technology Studio in Los Angeles. And he'll be talking about some of that more recent work. And Jeff is a professional engineer. He's also just finishing up his PhD at University of Southern California. And here to talk about a few projects.
Okay, thank you, Alex. Thank you, everybody, for some time today. My presentation is going to go through some of our philosophy on how we address parametric tools in our process, and then we're going to go through a series of case studies. Just a brief background on Enclose. Classically, we're a facade subcontractor. We like big, tall, large volume projects, lots of repetition, and we get involved during whatever phase in the project the contractor, the architect, the owner wants to bring us in. Classically, that would be at time for bidding a project. More recently, we have gotten involved in a design assist model where we come in early and we have kind of a two-phase contract where we help aid the design towards something that can be built, and then we construct it as well. So our core strengths are really in the field, actually constructing, dealing with schedule, quality time. And what I represent is the Advanced Technology Studio, and we have tried to build upon these core strengths at the front end and how we interface with complex architectural problems as well as architectural workflows. So I'm just going to run through some of the background and the philosophy and then hit the case studies. So about 5 years ago, a little bit over 5 years ago, we set up the Advanced Technology Studios. The first one was in Los Angeles. 2 years later, we set one up in New York. And really, this was a dedicated group towards exploring the cutting edge of advanced facade enclosures. And so classically, those previous projects you had seen had a lot of glass, a lot of aluminum, and they were flat. This group doesn't subscribe to those limitations. It could be a complex geometry, it could be something other than aluminum, it could be something other than glass. So really, when you dissolve what the materials or the enclosure solution could be, you end up with a group of people dedicated to focusing on process. And so really, our group, we try to blend a bunch of different backgrounds, all relevant to the process, and we try to have a diverse collection of people. And so this is a little bit of inspiration from Stephen Johnson's Where Good Ideas Come From. And in there, he alludes to the fact that great creative environments are like coral reefs. And a lot of this has to do with introducing diversity and allowing creators to collaborate together. And so in our studio, we have individuals. We're not overly large, and these numbers are just for the Los Angeles group. But we have about 5 designers, some engineers, some industrial designers in the background, construction management, strategic development, and really a clear connection to our marketing group, because so much of the complex ideas we want to explore require clear communication. And so our philosophy isn't new. We didn't try to create anything new. We tried to just sort of build off something that is really simplified that comes out of the Stanford D School. And it's really a design process for kids. And the steps that are in there have to do with empathy, defining the problem, ideating, prototyping, testing, and then using this model in an iterative sort of fashion. So really, the inputs in our process can change. And so our process then becomes a matter of how we listen, how we present options to the architect, how we develop new solutions, and how we test them. And ultimately, when we're exploring new types of materials or new combinations of systems, it's a matter of proving it and justifying it. And that comes through prototyping and testing. And so really, when you have this model that isn't repeating what the systems are from one project to the next, what then does become required is a group of individuals or that are adaptive and flexible, and it really becomes about agile minds and a willingness to evolve. And really, when we talk about the tools that we do that with, we're here to talk about our parametric workflows, but really the backbone of that is not a software. It's really individuals who are willing to think logically, organize their process, map out their process, and then execute, and be willing to work together. And so things like authorship of design have to be shared, and a willingness to sort of pull out what's the best ideas from your peers. So the actual tools that we use in our practice early on in the process, early phases, we'll use anything all the way down to Excel to manage data. We'll use other forms of database as well. For our iterative modeling, a lot of times we don't only do Rhino with Grasshopper, but a lot of times that's what the architectural team is using at the time we get involved. So we try to use the same tools and interface in the same platforms, but bring in sort of the constructability angle, not a design modification, but introduce constraints. And then during estimating, we use Revit as well. And once we get a project and it becomes secure and real, we end up modeling everything out in greater detail in Revit, and then using Inventor to sort of create each unit of our system automatically. And so we've developed some internal tools we call the e-generator, and it will take this information out of Revit and Inventor and automate the drawing of the part and the unit pieces. So really, this comes down to, it's not aluminum, it's not glass necessarily. We don't know what it is, but we know our problem has an input, we have our process in the middle, and we're delivering some outputs. So in this case, Grasshopper, I'm not sure how many people here are familiar with it, but it's a platform for kind of visually coding logic into a design environment, a three-dimensional design environment. And it can be used in a number of ways. It's really an open source platform where there's a lot of tools available online, where a lot of what you see here, maybe somebody's figured out a part of it and has shared it online in the 3D Grasshopper community. And then here, maybe I can stitch together several different processes. So all of these steps are dependent on the initial form that we see at the far left. So if we twist that form twice as much as we see here, all the subsequent steps will update automatically. So by mapping out this logic, we're able to sort of save time in developing iterations. So the first project has been completed, but is kind of on delay to open up. And this is the Fulton Transit Street Center in New York City. And the part we're focusing on here is the solar reflector show. And this the project is located at the corners of Fulton Street and Broadway in Lower Manhattan, and sees somewhere around 275,000 daily passengers. It's right by Wall Street. And so the project team was really developed by a collaboration between Grimshaw and Arab, and Jamie Carpenter and his group really worked on the central piece that we're going to talk about. So this is the initial preliminary renderings. The idea is to deliver daylight deep into the depths of a public space that doesn't otherwise normally get daylight. And the solution really ended up being a complex geometry. It's a doubly curved form. It has 952 unique panels. And what drives the shape of this are these 1,000 plus nodes. And all this information has to be managed, and it has to respond to the different loads, but it all happens over small square footage, only about 8,500 square feet. And so there's a lot of data points, a lot of lengths, and all these are unique numbers. So really we saw this as an opportunity to explore parametric tools for the first time in our office about 6 years ago. And this is just sort of peeling back the layers of the structure around it. There's a metal-clad dome that surrounds this doubly curved net that hangs from a skylight at the top. And all this is supported by a series of V-columns and primary structure. So the net hangs from the top, and daylight enters through that oculus at the top. So this is sort of our interpretation of the initial renderings, and then a couple years ago under construction. So we see that this is a confined space. This exterior metal structure, the metal cladding, really kind of obstructs and limits our ability to construct this shape. So the whole idea was we had to develop not just a way to manage the complex geometry, but to install this efficiently in a market that has very high labor prices. So from the beginning, we had a commitment to trying to bring out this cable net in one piece and hang it to minimize the amount of labor on site. And so just to give you a little bit of idea of the layers of the system, light penetrates through the south-facing skylight, reflects off these anodized metal panels, which have a varying degree of perforation from the top to the bottom. So at the top, they're more reflective and have smaller holes. At the bottom, they have larger holes, more transparency. And all of these connections to these panels were achieved with a single typical node. And so these paddles, what they were termed, are all the same throughout the field, but every condition that they're receiving changes. So the tolerance has to be built into this connection to allow for all the different conditions. And I like to say this is a typical condition on the project, which actually never occurs. So this is what that system ends up looking like. This is from the mock-up outdoors, so you get a sense of the light coming through. In reality, there's cladding behind it. But really, the mock-up is a great way for us to explore sort of the systems of engineering and how the Grasshopper and the parametric tool and the workflow would assist throughout the rest of the actual project. So as I mentioned, we wanted to hang the net from the top, and we were just planning to pool and make all of our adjustments down at the bottom level where we had better access. We didn't have to have field crews up the man lift. And so there's a series of 56 rods down at this level, and we were just going to adjust those to a set dimension for each of them that would equate to the total tension that we needed in the net. So at these perimeter conditions, you end up with these really intricate joineries of many paddles come together. And so, you know, this relies heavily on the tolerance of our fabricators to deliver these pieces, which is more like pieces out of a sailboat than it is out of what we normally do in architecture, or what we see in other enclosures. So early on, we were doing modeling of that typical paddle connection. This is a 3D prototype, and ultimately working with our vendors to provide real fabricated parts early to assist the decision-making process and gain approval on these pieces. So really, the foundation of the project are these 1,056 nodes. And we said we're going to relate every single step of the design of every drawing, of every fabricated part, back to this information. And the idea is when we get to the field, if these points have to shift around because the steel we're attaching to it is misplaced, which is almost guaranteed to happen, we can automatically update these points and verify that the system will still work or generate new lengths. So the relationship of all these panels within those nodes is a constant relationship we'll explore. So this is what our Grasshopper routine looks like. It's kind of the obligatory slide to show you the Grasshopper, but really it's a dynamic tool, but it doesn't do much good to look at it in a static form here. But the reason I really show it is we tried to partition our workflow here. So each of these clusters represents a different row within the geometry. That way we could, if we were identifying problems in the middle row, we could really quickly access the point in the routine to solve it. Because a lot of stuff is happening behind the scenes here as the computer just receives these points within it. So the less you can see, kind of the more at risk you are down there. So the question of input and process really changes when we're receiving the input and we're not in control of the accuracy of that input. So early on, the way we received that input was it was kind of a high security project. So we received all these 1,056 nodes as a image, not as a PDF, not as an Excel file, not as a model, as literally a 24 by 36 sheet on our table. So we need to be smarter than just to input these manually. So what we did was we scan these in, and we did a text recognition, and then we had an intern spend a lot of time filtering through to make sure all the sevens were sevens and not ones. But really, the real potency and potential for this is through model sharing, right? That would have saved us a bunch of time. So what our process looks like on this is we have these XYZ coordinates rounded to 1 decimal. And we saw the detail of those componentries. And we really need to be at a higher level of precision than that to work at that scale. So what we had to do was use this initial information, put it in, and then reverse engineer the true form and develop a new set of more precise points. Because of this holdup in the process that we weren't going to get these data points truly from the engineer. So once we had these, we were able to do all sorts of things like visualize the geometry and do takeoffs. This is just during the pre-sale phase. These are the kind of things we're producing to get vendor quotes and to work with our sales team. Then we get the project, and we go through this exercise of structurally engineering it. And so the net is tension, and each row is prescribed a different tension. What we see here on the right is the top 3 rows get one set of tensions, the next row gets another, et cetera, et cetera. But just like the accuracy that we required on the nodes, this even distribution isn't true to what the net's going to find its form to be. So this is our starting point. We use those initial nodes. We use these initial tensions, and then we develop a higher level of information. We generate what the specific tension is on each one of the little cable segments throughout the net. And we have to do this iteratively until we find the reverse engineer the geometry back within the tolerance that we're going to be held to in the field. So what we do is we end up using our structural analysis program, Excel and Grasshopper, and we do this loop, and we try to get it to the point where we generate the 56 values at the bottom that we can pull on the bottom rods that will equate to the form that the net really wants to be. So we did this analysis, and it took about, fortunately not too many, it took about 4 iterations before we could get the deflection or the displaced values from the desired locations within tolerance. And so after those 4 iterations, we were good in one direction and over 90% were good in the other. So really our process here is with the deflected shape, we end up with these feedback loops. So this is sort of our nomenclature in the studio for thinking about parametric workflows. Within the process, before we sort of wrap up this subroutine, we end up coming back around to the initial step. So after we get the deflected shape, we're bringing a new set of information back in as our initial input until we end up with something that's resolved. So really, the real value of this tool on this project is in fabrication. And you have 952 unique panels, and I said I don't want to draw 952 panels. I'd rather spend a week drawing or coding or mapping the logic out once and then letting the computer do the work. That's really the value here. And it's me being selfish. The tool just helped me. But here you see sort of the relationship of the nodes to the panels. Each panel is an offset of the center lines between 4 adjacent nodes. You end up with these rhomboids, and then it is a doubly curved shape, but the panel, being metal, is planar. So it ends up getting folded along the midline. They're fabricated flat and then folded in the field. And so in the model space, really what we need to do is take the panel, unfold it, and then place it flat so we arrive with a series of pattern cuts, what we see on the right. So this really summarizes our process. We have the Excel data that is our input into our Grasshopper routine. We have each one of these clusters as a row, spitting out all of our panel drawings. And the level of information that we're producing is not that complicated, but it's happening really quickly. And what we get is dimensions that we can then coordinate with our panel fabricator. Now, truth be told, the real value of this was to automate the panel generation. Because of working with a vendor who, just because of legal issues, we weren't able to just give them our stuff. They went through their whole process of coming up with their own panel geometries and their panel set information. But what this did end up doing was allow us to do quality assurance. We would just do side-by-side checks like that. So there's still opportunity to take this further, closer to file fabrication. So then, mock-up and prototypes, that's really what we live by. And really the challenge here was not engineering, not creating all these 952 unique panels. It was, how are we going to build this thing? And so this is the cable net, what it looks like when it arrives on site. This is up in the shop in Massachusetts at Tri-Pyramid, who developed all the cable componentry. And so what we did was, before we showed it to the architectural team, we did a practice lift in an outdoor environment that had no enclosure around it. So if we couldn't figure it out here, we didn't stand a chance in the field with the metal enclosure around us. So really, the way this comes to life is the field superintendent, who's responsible for building the job, develops this temporary rigging ring that the cable net comes in, it's attached to this cable ring, and then there's these lifts that lift it up, and then it gets transferred from this temporary ring to the final ring on site. So it all works good, then we bring the architect and the consultant, we show it to them, the owner, they have buy-in, and then you get to the site and you pray it works as smoothly as it did out there. But before we get to do that, the parametric model was very helpful in assisting in survey processes. The rings at the top and our interfaces are almost always off. They're off by some level. The tolerance of primary steel compared to the tolerance of these stainless steel fittings are very different. So what we decided to do was we're going to fabricate everything within the net and ensure, just hold the initial geometry to be true. And then we get out to the field and we make adjustments only at the bottom rods. So we were limiting the amount of adjustability that was dependent on the field measurements to these 56 rods at the bottom. So we waited to fabricate those at the end. So these are just some diagrams of the temporary rigging that was used to lift the net. And then this is the net hung in place. The cladding was then a second pass, but the net required a much larger crew to hang than the number of crew members to hang the panels. So one thing where the parametric tool and 3D modeling and clash detection, it doesn't always work out perfectly. And these are some of the honest tales. This is the HVAC duct that we see here behind the net. We had some pretty detailed Navisworks models that were coordinated. There's some concerns on site that maybe this HVAC duct is going to interfere with the net. And when they did the clash detection in the model, everything was good, But our project manager didn't trust the model. He trusted his eyes. And when we went into the model and we really simplified it and looked at it in 2D, it was really just a modeling error. The diffusers on the face of the HVAC weren't modeled to the level of detail that they actually are. And so here we can clearly see, just in a simple two-dimensional drawing, a problem that the 3D model missed. So when you're collaborating and you're blending models, you really need the level of modeling and accuracy to be consistent across the parties. Another error in the field, all the components were supposed to come out tight, and some of them got jostled during delivery and they were loose, so we had to send crew members along the top to tighten every single one of the rods at the top. And at that point, you're having them readjust something that you have to 3 decimal places. You're telling them, they don't care about 3 decimal places. They know an eighth, they know a 16th, they know a quarter. So really, the precision of how it gets done in the field is the accuracy of this gentleman's thumb or his eye. So we really had to, we could generate complex data all day long, but really simplifying it and delivering it to the field teams is more important. So then the net gets hung, it gets tension, it's in place, and we start cladding. And really, we know the net's going to be off, but we have tolerances that we're going to be held to. So really, the whole story visually on how you're going to believe if the geometry is correct is the gaps between the panels and the visual that these gaps look consistent and maintain consistency across multiple panels. So we ended up spot checking about 10% of the panels to prove to the architectural team that the net was in the right place relative to itself. So the real power of having some of these models and working with the individuals who are going to build this structure is trying to convey a system that they're not used to installing, installation strategy that they haven't done before, and maybe studying some of the on-site constraints that you can't really get when you're practicing in the parking lot at the shop in Massachusetts. So on-site, there's an elevator core that really limited the ability to get the net hung in one piece. So it really required a very high level of almost like an orchestrated rotation that we'll see here in a second. But this is how we sold this story to the ownership to give us clearance for a whole day to have the space just for us, not for other trades, and that we were going to get this done. So we animated it. We used these models. The model lives throughout the life of the project, and it actually tells a story and educates on safety and installation methods. So here we're taking the parametric tool, and we're using it in a true kind of application constructability driven way. And so this sort of breaks down sort of the configuration here. The net came in as one piece. It gets assembled here, this temporary ring, and then they start to peel the net, unravel it, and attach one ring at a time. And so this is great when you have a project completed and you have the imagery from it to kind of see how the tail up front ended up being the reality in the end. So the net arrived on site around 7:30 in the morning, and the net was hung by 11:30 a.m. And so yes, we have maybe a crew of 4 times the number of people we normally have on site, but it was just for that morning, and then we had sort of freedom to install the panels as we pleased. So for just some of the computer modelers out there, animation was done in Maya. So we took our grasshopper models, we baked it into Rhino, and we brought that into Maya to start to animate the sequence. And so the individual, this goes back to sort of about the studio, the individual who helps to do these animations, he's an industrial designer background. He would have otherwise gone to the automotive or video game industry, and he's been part of our team for 5 years, and he's part of our workflow where we have collaborating a modeler, designer, and then he's helping to tell the story. And it really comes down to that field superintendent working with this visualization specialist very early on to build this whole narrative. So the project was supposed to open up at the end of July. It's been delayed at least 3 months, so that would put us at the end of September. The net's been done for about 1.5 years itself. So if you get a chance and when it's open, I encourage you to visit it. And so for our process, we weren't really in control of our input. We ended up using parametric workflow from estimating to structural analysis through fabrication and mock-up. And the sort of recipe of tools we had were Grasshopper, Rhino, SpaceGas, which is our structural analysis tool we used here, and Excel. And then we gave it life through the installation. So this is the initial vision, the vision of how it would get constructed, the reality of how it got constructed, and then the final product. The next project I'm going to talk about is the San Francisco Museum of Modern Art. This is a project designed by Snowhetta, and we got involved in this about 6 months before we got the project, and we were way over budget, but we were in a better position than our competitors. And what we had to do was go through a 6-month exercise back and forth, meetings in New York, meetings in San Francisco, to really pull out 40% of our price for the envelope that you see here. And this is the initial architectural vision. And the architect really had a desire to use a material called fiber-reinforced polymer, because this gave a lot of flexibility to CNCing the shape of these panels on this ripple wall that we see here. Now, in addition to that, the architect wanted to use the fiber-reinforced polymer in the flat surfaces as well. So this was kind of a contradiction to what the material strengths truly were. The project is an expansion to an already existing museum. It's a very, very tight site. And the initial concepts that were developed by the architectural team and the facade enclosure team really required a lot of field installation, on-site installation. What we see on the left is sort of a stud wall with panels placed on top of them, so we have multiple passes in the field. We have the construction of the performance barrier itself, and then another installation for the horizontal banding panels. And then on the right, the other idea was, what if we made large precast panels about 32 feet wide by anywhere from 12 feet to 24 feet tall, without really any consideration of where the crane may be set or how we would ensure performance of that backup barrier. So where we started was we went to the architects and we listened to them, and they said that they wanted this fiber reinforced material. And we said, we want to unitize the backup system. We don't want to do this field construction. So we kind of had our priorities on the table from the very beginning. So we went back, spent some time coming up with a system that used an opaque backup performance units, similar to our current wall systems, just without glass, stuffed with insulation, and then we'd come back and take the fiber reinforced polymer panels in a second pass on the exterior. Now this still didn't solve the problem of having multiple passes in the field. And because of the geometry, we end up with these interfaces between units that aren't typical towards a flat construction. So we end up with some jogs and some angles between our transitions. We end up going with a couple bellow gaskets here at our stack joint to kind of remedy some of the performance issues along that key seam. So these are the kind of visuals we generate early on to help communicate the system of the units coming together, how we attach to the floor. And then we end up coming up with a strategy that would get us within budget. They give us a job, but the ramifications are we end up with, some revisions to the apertures within the geometry. And on the flat walls, since actually the cost of fiber reinforced polymer in a flat application was more expensive than in a curved application, because the flat application required stiffeners as backup, where the curvature in the other solution gave it some inherent strength. So we ended up in one meeting saving a big chunk of money by saying, let's get rid of the flat fiber reinforced polymer and let's do a white glass instead. And so this required the architectural team to be flexible, to understand the budgetary constraints of the project and the inherent strengths of each material. So the FRP is limited primarily to this east facade and then some small portions on the west facade. So here, there's a lot going on in this geometry that is continually changing throughout the 6-month design assist process. So what we tried to do is deliver a clear plan early on how we would work through the architectural priorities as well as ours. So the first part was performance, this backup barrier that's going to protect the museum, everything that's inside of it. So we said, let's forget about that contoured, rippled surface for the moment, and let's set our interior surface based on interior programming requirements and go from there. And so really what this started out with was setting our stack joint location and working and offsetting those from our edge of slabs. So this was the very first sort of back and forth with the architectural model, taking these initial limitations of where the interior slab could be, understanding those and trying to resolve those so that the performance layer could use as many flat panels as possible, minimize the amount of unique panels, complex panels. So from these slab edges, we end up generating a base opaque surface for stud. And from this, we then start to subdivide these vertically to generate units. And what we do here, what we see in red, are units that end up being warped or heavily warped or requiring some sort of transition or fold in them, something that couldn't be fabricated flat. So what we wanted to do was take this backup system, these unit geometries, and try to, we just threw out a number. We said 80% of them need to be flat, and that'll equate to this price. And so we probably started at 20% of them being flat and 8% being warped, and we had to reverse the model here. So the way we did that was we studied subdividing it differently. On the left, we see 8-foot wide subdivisions. On the right, we see 4-foot wide subdivisions. This allowed us, with the 4-foot wide, we could limit the warpage to something that we could actually do in the field What the project ended up at was around 5.25 feet wide units. But really, we're starting to see some key zones in red there that became the focus of our back and forth exercises. So really, to get over the hurdle and get to our goal of under 20% warped units, we had to take a different approach. We had to say, we can't have some warp here throughout the entire field. What we said is we need zones of planarity, and then we need transition zones. And we'll introduce transition zones as often as we need. So these red bands end up being our transition zones. And we said, instead of taking this performance barrier and warping it in the field, we'd rather articulate this fold in the shop and ensure that our seals are of high quality. So this ended up being how we achieved that with these folded zones. So we delivered this to Snowhetta on the top left. Snowhetta came back to us and they said, this zone in this brighter blue here in the middle top, that zone, we need to kick it out a little bit more. What do you think about doing this? Rotate it about this point. And so we would go back and forth with rhino models that were all being baked out of Grasshopper. So here, we ended up setting that backup performance layer surface. So that worked with everything they had going on inside, all their slab edges, all their programmatic space, all their circulation zones. Now it was just a matter of working outwards from there to generate the rippled surface. So the way we went about that was we created a zone of overlap between the FRP and the backup system, and then worked with Chrysler and Associates, who is our vendor who fabricated the FRP, worked with them to generate how far out could Snowhetta take this rippled surface. How much space did you need to offset it to provide a zone for backup support structure? And then how contoured could those ripples be? And so they set those limitations. We provided that to Snowhetta, who worked with Gary Technologies to develop the desired ripple surface. We would then receive that back. We would review it. Chrysler Associates would review it. Once it was acceptable, then Chrysler got the green light to go ahead and start CNCing out each of these units, generating the returns that allowed it to attach, etc. So to start this process, we needed to understand where the desired geometry was for the ripple surface and how much offset they were really looking for. So on the top left, we see an 8-inch offset zone that equates to, if you see the gray, we need to come out further. So then we have a 12-inch and a 16-inch. And we ended up seeing that a 20-inch zone for them to play with was what they needed. Now, 20-inch zone everywhere, would have had cost ramifications. So we kind of, once again, negotiated with them and said certain zones are okay to go that much. So we see the development in the top left of the base geometry, the overlap systems in purple, then the 20-inch FRP zones, and in the transition units themselves, we pulled them back to 12-inch because we had to consider the space required to do that transition. And then in the bottom left, we see the overlay of the desired ripple surface occurring within these zones. So then we end up with this master surface. And then we get the go-ahead to subdivide these vertically, and this allows the fabrication to initiate. So the way we end up dealing and tracking progress throughout this design assist doesn't really work naturally with some architectural teams with a classic Gantt schedule. So what we did was we developed a system of mapping priorities and decision making that we just call priority workflows. And what we see here is on the far left kind of the highest priority issues, and on the far right kind of the deliverables that we're going to be held to. So what we said is we really need to set these slab edges, we need to set the stack joints, do all these really regimented, boring constraints before you can do all the exciting stuff with the ripple surface. And if we make progress there, then this is how we're going to meet our deadlines. And so this tool is one that we kind of created on the fly for this project. And then when we talk about the apertures, all the glass within it, working with the consultants as well, there are so many considerations for the quality of light coming into different spaces depending on the art behind it. So there's lots of glass options as well being considered. And we use a matrix like this to kind of have that back and forth with the team. So the FRP panels themselves, they're CNC milled out of polystyrene, a negative of the shape. These units are about 5'3" wide by a maximum of 24 feet tall. This is an example of a mold for a warp transition unit. And then this is a unit just outside the shop in Napa Valley. This is the series of mock-ups we did. On the far left, a visual mock-up, and on the far right, performance mock-up. And then this is just on site last week. We see the delivery and bunking of the units in the top left. We see the scale of the unit adjacent to a crew member in sort of the middle top right. And then in the top corner on the top right, we see a seam on the back side of one of the folded performance layers. So I kind of skipped over it, but really what made the difference was we ended up taking the horizontal banding of the FRP units, rotating them vertically so that we could mate the FRP to the backup unit in an assembly shop and just do one installation pass in the field. That was the only way we could get the budget to work out with the money they had. So we ended up working with the architect, and they were really flexible on orienting the surface and the joints vertically instead of horizontally. And this is a progress shot of that effect. And so what became really important was the transition between units, the width of the vertical joints, the tolerance of these curves, and really this FRP material and Chrysler and Associates' ability to fabricate with CNC to this precision is pretty phenomenal. And then this is a corner shot of the building with the FRP east elevation to the right, and then the flat opaque white glass on the left. So this is a project for Amazon, their headquarters in Seattle, Washington. It's a very organic primary structure. It's 3 differently sized spheres that interlock with one another, and it's based off of a Catalan grid. So though it looks pretty wild, it has each sphere has repetition within it, and the glass is all triangulated and flat. So here, what we really need to do was make sure the glass slides were within construction limitations from glass suppliers for insulated glass units. So here we sort of see the subdivision of within each of these dark perimeter frames, these pentagons. This is kind of a family, and that family repeats kind of like a tessellation on a soccer ball. And what we did was, using Grasshopper, we tried to identify all the truncated lights, all the atypical conditions, and ensure that they were either big enough to be fabricated, because there are lower thresholds for insulated glass units, or make sure that all the lights were within the maximum dimensions. So we used Grasshopper to take all these planes oriented in different orientations in space, flatten them, put them within limitation boxes, and verify that they were acceptable or not. And so when we found a light that was not acceptable, we would take it and we would rotate it 360 degrees and use a routine that would try to force it into the limitation box. And we would either find that it does fit or it does not. And then once it does fit within the limitations of what's fabricatable, it would produce the various options that would make that work. So here we have routines that we can use from project to project to really work with the architect early on to say that revised geometry is within limitations, is within the constraints of vendors. Each vendor has different constraints, so if we can set that parameter in the routine, we can do these checks very rapidly. So then once we have the glass subdivision where it needs to be, it becomes a matter of offsetting the structure to generate the primary, the secondary frame for the glass to be supported. And each sphere sort of is scaled proportionally, so the primary structure on the larger sphere is larger than the medium as well as the small, and so is our secondary frame. So what started to become complex is always the atypical conditions, the interfaces with other trades. So here in this case, it was the anchor conditions between spheres. So we used our Grasshopper model to set up a logic of what those rules were at these anchor conditions, and then we let the routine carry itself out to model all those various conditions. So here on the right, we see the interface of that anchor at the primary structure. So just last week, these are some shots from our visual mock-up. We see the primary structure in gray behind the white steel frame. And so these are some of our views of our mock-up drawings. And then this is what it looks like. The steel contractor on this has his work cut out with all that bending. But it's really impressive steel. And then on the left, we see the interface between our two systems. We have this 3.5-inch diameter threaded anchor that the geometry of the primary steel related to the geometry of our planar frame is really what the key coordination item is for us in the primary structure. So these mock-ups are so important to learn what things go smoothly and what things don't. And you can't anticipate for the difficulties. So here we see the installation of the glass lights. And then this is, it's not sealed. It'll be field sealed this week, but this is the visual mock-up that we'll show to the owner and get approval on. So this is about 35 feet tall, about 25 feet wide, so pretty large. And so once again, we have a story that we're trying to sell on how we're going to construct this. And we're using these same models that we use to do these studies to generate this storyboard. And here, really trying to articulate the concerns about interfacing our anchors with the primary steel. We're concerned about access to the underside of the sphere, having limited access, so we'll need to use different equipment to install the lights on the underside of the belly of the sphere versus the lights on the top. And that's what we're trying to convey through these visuals. So the contracts that we end up working with on these projects is we end up going through all these efforts, these visual mock-ups, and really the architect and the owner still have the ability to pull the cord and go with another facade provider in the end. And so we really need to tell a unique story that is advantageous to us, that we can construct better, that we've thought out more detailed, so that we can price it more detailed, and really be responsible with how we're selling our construction scheme and the price for that. And so, we'll go through 6 months, 10 months, 12 months of these efforts, and we have to work in a way to kind of make sure we can perform the job in the end. So I won't narrate too much on what's going on here, but the whole idea here is to use tools that are familiar with the architectural team to communicate these ideas. Be willing to receive model information in a number of different platforms from an office such as yours, and then introduce limitations and constraints that affect how it gets built or making it a real thing. So when we talk about model sharing and items like that, or sharing grasshopper routines, it's really in the spirit of delivering that next step of constructability and feasibility. And it's not about modifying design. The initial concept versus where it is now look very, very similar, but the amount of detailed study and exercises are very intricate and are required to make a job real. So for the sake of time, I'm just going to go through this project quickly so we have time for questions. This is the Academy Museum of Motion Pictures in Los Angeles. This is a project we spent the first 6 months of this year working with Renzo Piano's group on trying to develop an enclosure scheme. And we'll focus on this dome on the left. And this dome looks pretty regular, but the problem is instead of subdividing it radially or in a meridian type fashion, it was sliced like a loaf of bread. So when you do that to a curved surface, you end up with tons of variance conditions. So on the top left, you see the subdivision of glass that the architectural team initially had with the consultant. And there are some pieces of glass there down that center spine that are 32 feet long, 8 feet wide, doubly curved, and not fabricatable. And so what we did was there's really only one fabricator in the world who was able to execute this glass within the constraints of this project, and they have to melt the glass into place. They have to slump the glass. And so what we did on the right was we introduced some studies based off of the limitations of what that company could do. It's a company outside of Barcelona named Precursa. They do phenomenal work. But another challenge was we couldn't really support a triangular glass light because triangular glass lights, in the way that they were being supported here by points, would end up having real high stress concentrations in the corners. So we wrote a grasshopper routine that would take a triangular light and try to make it one with any of the adjacent trapezoids by it. So we would end up with a pentagon in the end, and then it would study if it fit within the dimensional constraints. So when the geometry is changing every couple of days, having these routines where we can check, set up, really saves a lot of time and gives that feedback loop to the project team quickly. So this is the development of the structure. Won't go too much in depth here. And once we set this, there's a cable grid underneath, and we model all these logics to populate the form, the model space on their own using Grasshopper. And so where this project ended, they had some budgetary issues. They're going back to some redesign, but it culminated, our 6-month phase culminated sort of with a development of system designing, turnover of 50% DD, 100% DD kind of drawings, as well as a series of prototypes. And this really gets back to our philosophy about prototyping to assist decision making, because the prototypes we developed here, almost the second you put them on the table, in some fashion, they become obsolete immediately. There's some flaw that doesn't read in the model space, but only reads in physical form. So we worked with our vendors to create prototypes like this to study how the horizontal member comes into the primary member. What's that weld look like? What can our vendor deliver on the quality of that weld? So just in a piece like this, we end up sort of pulling together anywhere between 6 and 12 vendors. You have a different vendor for the steel, a different vendor for the cables, the cast stainless steel items on the bottom, the painter, in this case, instead of glass, the plexiglass. So these are sort of quick turnarounds. We had about 6 weeks from getting approval on our prototype to delivering not just these guys, but this whole room of prototypes. And so we study both in true material form, like the steel prototypes on the left, and then this white mass in the middle is actually a 3D printed prototype. So we try to explore different avenues to put things on the table to accelerate decision making. So just to wrap up, a couple of the key takeaways is that for parametric workflows and in a collaborative environment to work, there really has to be a commitment towards design collaboration. This means being willing to model share, thinking logically, working with constraints, embracing the constraints, and then really studying the right materials for the geometry or for the project or for the budget. And really just something that has perplexed me the last year is with projects like these, we're able to produce so much data, generate so much information, get it down to the 3rd, 10th decimal place, but the Fulton Street came down to the installation of a field member locating something with a tape. The AMP project at the end, that came down to the quality of a weld. The SF MoMA project, we're able to print and CNC these molds, but the FRP is still hand lathed by individuals and the resin poured by individuals. So craftsmanship is really what makes these things happen, right? The precision of those joints is dependent first on the geometry being set, but ultimately carried across the finish line by the craftsmanship and then the field execution. So these vendors are really key relationships. So that's my story for today. Thank you. Any questions?
And I was just going to say that people that are in other offices, just please go ahead and speak up if you have a question.
We had some questions back here. Maybe we can pass the mic back.
Your presentation with the importance of prototyping, which clearly is an iterative and costly component of the design. And you mentioned when you started that you enter the process at different junctures based on where the architect and owner are at. In the examples that you showed, were you engaged in the process similarly in each one? And the question I'm really wondering about is, to what degree do you all take a business risk in some of your complex parametric development in order to embed yourselves in the process and become the fabricator and installer? And or do you also work in a conventional consultant type relationships where you're brought on as part of the team and have a consulting fee in order to work on this level of development and prototyping?
It's a great question. The first part of that, for each of these projects, it was a different model. So the San Francisco Museum of Modern Art, we worked for 6 months at risk with no guarantee of getting the project. Now, in the end, we got the project, The Academy Museum of Motion Pictures, we worked for 6 months and we got paid. Not as much as we spent, but we got something. And the Amazon project, we also got a design assist fee as well. Now, we don't make any money unless we build it, and that's what it comes down to. So the way we can sustain that and that investment is these are portfolio pieces that are complemented by more traditional, less risky projects, right? And those our company is a similar size as yours, and we're talking about 2 studios of about 15 people on each coast that represent kind of these intense explorations, but there's also straight, flat aluminum glass curtain walls that we love building as well. Yeah.
I'm just curious about the nature of model sharing with various architects that you've worked with and how that's worked from a practicality standpoint and from a legal standpoint.
Yeah, there are some projects that I can't present today, like the World Trade Center Calatrava project, the Transit Hub in New York, that, the security on something like that, you're not getting any model sharing. The Fulton Street project, you're not getting any model sharing. And it's interesting because it's a one-way model flow, it seems like. Owners or the architect will require that we provide model to them, but not a willingness to do it in return. Now, in that San Francisco Museum of Modern Art, we were involved so early, and they were so disconnected from where the design needed to be for their budget that model sharing was embraced and it went very smoothly. The way that worked was they're kind of called data dumps in the industry. You kind of work for 2 weeks and you back up this truck and then you offload your model onto the consultant or the next person downstream, and then they check it. And so you have to work through these cycles, and usually by the time you get to that deadline, the architect's already got another idea that needs to be updated into that. So we're kind of on these overlapping cycles where we're kind of spending 2 weeks to catch up with it. But legally, it's an issue, and it isn't used as a contract document in most instances. Yeah.
Did you contractually end up having some sort of an indemnification with each other when you were doing the model sharing, or how did you handle that contractually? So as the architect wasn't assuming some of your risk and vice versa.
Yeah, so, I mean, sometimes the legal issues obstruct the progress of a job, and sometimes the design assist model works best when there's not a contract in place. And so the general contractor in the SF MoMA case was present for every meeting, didn't say much, intervened when necessary, but supported the workflow and understood the workflow enough, and it had to be trust and shared risk at that stage.
I'm curious to hear a little bit more about the transition from doing the more kind of large-scale, commodity-driven work to these specialty studios where there are unique projects that came up that made the company realize that they needed to develop these specialty units, and how did that go down?
Yeah, so before working at Enclose, I worked at a company called Advanced Structures Incorporated in Los Angeles. And in 2007, Enclose acquired that company. And that company focused on a lot of projects like this. They were design build, they high transparency, not very many subcontractors willing to take on the risk. So this was a notion that the owner of Enclose said, we're doing these towers that have these jewel boxes at the base. And those are the exciting parts, you know? What if we were able to have a competitive advantage and deliver both of those to an owner or both of those to a general contractor? So they acquired that group in 2007. The market kind of went south, and our competitors were willing to cut their margins on typical projects because there's less and less of them. And so the projects that sort of resurfaced first after that downturn for us were transportation-based projects with high-profile architects that were taking these geometric risks. So we didn't have a choice, really. The market forced it, but we went all in and said, this is a great time to reinvest in these competencies so we come out a step ahead rather than playing catch-up.
Controlling a character for someone, you know, you have to spend a lot of time building a rig before you animate. Right. That's exactly it. So,
I had a question that might not be a quick answer, so if it's not appropriate, we can talk offline.
Sure.
So you talked mostly about geometric constraints, some structural constraints, construction sequence constraints. Can you talk about if there's energy constraints or things that plug into light models or things like that that govern some of the parameters?
Yeah, there definitely are. And the energy component often falls into the laps of the facade engineer consultants or the energy climate consultant on a project. So these project teams, by the nature of these different performance issues, become very multifaceted, many players involved. And so it's just like those cycles I was talking about with the geometry and the form. We'll go through something like that class matrix I showed, and we'll have to provide all sorts of new types of information that we didn't have to before about color index and things that would affect a statue differently than they would affect a painting. And it's in California, so you have Title 24 issues. And that is such an evolving facet of performance that it gets its own specialty consultants. So we work with them, but a lot of times we're the link between the vendor's information and what's available and what they've modeled and what needs to be coming out of the system.
Yeah, I think I'm going to stop it there because we're a little over time. But thank you so much. This was a really great conversation. Appreciate you coming by.
Yeah.